Hi folks, today I want to talk about some stuff with functions. We're going to talk about domain of a function, we're going to talk about some operations with functions, and composition of functions. I'm going to kind of talk a little bit about all of those topics. So before I get started though, I do want to talk a little bit about what's kind of coming down the pike. All of these things are in preparation for the more upper level mathematics that we're going to be getting into. So a lot of this stuff should be familiar to you, but it is necessary that we review it in order to start doing the other things that we're going to be doing as we progress through these units. So the domain of a function, that shouldn't be something that is completely unfamiliar to you. I know we haven't talked about it in much detail, but we did talk about it a little bit earlier on. But I'm going to talk more about it now, especially in relation to when we're performing algebraic operations on functions. Remember that domain is simply the largest set of real numbers for which the function is a real number. And so if you think about that logically, you're saying, well, what are all the x values that you can put into a function that will spit out an answer, so to speak? And if you kind of think of it that way, then you can say, well, that kind of breaks it down and makes it a lot easier. For example, if I have f of x is equal to 2x plus 1, you should look at that and you should be able to say, well, I know that's a linear function, and I know that there are no restrictions on linear functions whatsoever, which tells me that my domain can be anything, so it would go from negative infinity to positive infinity. Right? That's very straightforward. If you're looking at a function that is not linear but is quadratic, something along those lines, you should also look at that and say, well, there really aren't any restrictions on what I can plug in for x. X can really be anything. It's always going to give me an answer. So again, my domain would just be everything, all real numbers from negative infinity to positive infinity. Those are very straightforward examples, ones that you're already familiar with. It's when we get into more advanced type of functions that we have to be a little bit more careful. When we are dealing with root functions, more specifically even root functions, because you can take the cube root of a negative number or fifth root of a negative number, right? Those really don't have any restrictions, but when you're talking about taking the square root of something, you know that that has to be, when we're talking in the realm of real numbers, we know that that has to be greater than or equal to 0. So I know that this, x minus 4, has to be greater than or equal to 0, which means x has to be greater than or equal to 4. And so if I were to write that in interval notation, that would mean that x can be anything including or equal to or greater than 4. Okay, so those are pretty straightforward. Let's talk about higher level functions though. Let's talk about polynomial functions. A quadratic is a polynomial function. A cubic is a polynomial function. Any nth degree polynomial is a polynomial function. And honestly, there aren't any restrictions on just plain polynomial functions, right? I could have f of x is equal to x to the 4th minus 7x cubed plus 8x squared minus 10 or something along those lines. There are no restrictions on what I can plug in for x, and I could have any degree equation up here. But if it's a polynomial function, it's going to exist everywhere, so your domain would be all real numbers. Whoops. All real numbers. When we start talking about other things that we can do with those, when we start talking about rational functions is when you have that function where you have variables in the numerator, denominator, or both. So for example, if I had x plus 2 over x minus 5. Well, I know that this exists everywhere except at 5, and so I would have to exclude 5 from my domain. And so if I was going to write that, I would say, well, I can go from negative infinity to 5, and I can take the union of that with 5 and positive infinity. So this is including all numbers except 5. When you start getting into those rational functions and those even root functions, that's where you have to be careful about your domain. Okay? Let's talk about combining functions. We can perform any type of operation we want on functions. I can add, subtract, multiply, divide. I can do whatever I want on any type of function I want. So for example, if I have f of x is equal to 2x plus 1, and I have g of x is equal to x squared minus 4, I can do f plus g of x. Right? I can do f plus g of x. All that means is that I'm adding my two functions together, so 2x plus 1 plus x squared minus 4, right? And that would give me x squared plus 2x minus 3. Pretty straightforward. I can do the same thing if I'm subtracting. F of x minus g of x. That's 2x plus 1 minus x squared minus 4. Here's where you have to be careful, because you have to be careful with that negative. You end up with negative x squared plus 2x plus 5. Okay, you have to be careful because you have to distribute that negative. Multiplication of functions fg of x just means you're multiplying them together. 2x plus 1 times x squared minus 4. And you just FOIL that. 2x cubed minus 8x plus x squared minus 4. And if you just clean that up, 2x cubed plus x squared minus 8x minus 4. Very straightforward. Notice all of these are polynomial functions, so there are no restrictions on my domain in any of these. It's when you get into dividing your functions that you have to be very, very careful. So for example, if I have f over g of x, or f divided by g of x, I have 2x plus 1 over x squared minus 4. And if that is in fact my function, and there's nothing that I can do with it, then that's what it would be represented as. However, you need to exclude values from your domain that cause that denominator to be 0. So you would say, well, x cannot be plus or minus 2. If in fact you had a situation where you could reduce this, you would have to exclude the values from the domain before you do the reducing. What I mean by that is this: if you had f over g of x, and that gave you x minus 3 over x squared minus 9. And some would say, yeah, but you can factor that. You get x minus 3 over x minus 3 times x plus 3, which in fact you do, right? And you can cancel those, and that gives you 1 over x plus 3. So you would say, well, then I would only have to exclude negative 3 from my domain. But that's not true. You have to go back to the original, because this is where you would be starting. Somebody might try to solve it before they reduce it, and you have to take that into account. So in fact, you would say, well, this the restrictions here are x can't be plus or minus 3. Okay, So that's just a quick little thing about combining functions. Let's talk about composition of functions. This is something that should also be familiar to you. You have done it before, but we'll do a quick review. I'll actually use the same two functions that I was just using. I think that's what I was just using. Maybe it was 2x plus 1. Doesn't really matter. Okay, a composition of functions, that simply means you are, instead of doing like f of 5, right? F of 5 would tell you, well, hey, just replace x with 5. 2, 5 plus 1, plus 1, which would give you 11, right? Well, what if I said, well, tell me what f of a is? You would say, well, that's easy. I'm just replacing x with a. That would be 2a plus 1. Good enough. What if I said f of x squared plus 1? You would say, well, that's easy. Just wherever I see an x, I'm replacing it with x squared plus 1. Right? That gives you 2x squared plus 2. Composition of functions is exactly the same idea in that you are replacing x with a whole other function. So in this case, I am replacing x in the function f of x with the function g of x. So I end up with 2 times x squared minus 4, because that's what g of x is, plus 1, which would then give me 2x squared minus 8 plus 1, or 2x squared minus 7. Okay, composition of functions is just replacing the x in the first function with the other function. That's the whole idea behind composition. Okay, you'll see it, the notation written like this, f of g of x. You'll also see it written like this, f circle g of x. It looks like fog, kind of. They're both acceptable notations. You'll just see, you'll see both of them. So f circle g of x, that's how you would say it, is the same as f of g of x. And now, because we've been talking about domain with those other functions, let's talk about the domain of the composition of functions. So the domain of this composition of any f of g of x, okay, is the set of all x. So it's all x values that satisfy two conditions. The first condition is x is in the domain of g. Okay, x is in the domain of g. So x is in the domain of that inner function. And then g of x is in the domain of f of x. Okay, I'm actually going to stop the video there. Just because I'm running out of time, I'm going to start a new video and I'll do an example of this to kind of wrap this stuff up. Okay, thanks guys.